In this video, I want to briefly talk about the major changes in the layered organization of computers over the years, starting with the introduction of digital computers in the 1940s. But before we do that, I first want to review the layered architecture that we come to expect today. So at the lowest level is the digital logic layer, where bits are combined to make registers, and individual logic gates are put together to provide a functional unit that can perform the AND of two values in registers, or the addition or subtraction of two values in registers, or comparisons. Above this, the microarchitecture layer organizes the functional units of the logic layer into something that's a cohesive structure for executing a large series of code. And above this is the instruction set architecture that is exposed to our programmers. And this is the lowest level of programming that we can be exposed to. But we don't typically write at this level because it's very difficult to do anything. We must deal directly with the specifics of that architecture. What we introduced to improve our capability to program is the operating system layer. And that layer not only provides some security to prevent us from doing certain types of instructions that change big system-wide parameters on our computers, but it also exposes nice new APIs that provide something like a virtual machine by which we can program sound cards, networks, and things of that nature. Above this is the assembly language layer. Now this is the first practical low-level layer at which we write software today, but we don't do very much writing at this level. Instead, we tend to write in high-level languages which are translated down to assembly and machine language and execute on top of the operating system. Or we write in a high-level language and execute that code via some kind of interpreter. Now in the 1940s, computers were certainly complicated, but their layered structure was actually quite simple. There was the raw digital logic, where the gates were put together to perform specific functions, and the only instruction set that was available was one where we programmed everything in the direct ones and zeros of the logic, effectively providing voltage levels here and there where needed. And most of the time the programming was done by connecting jumper cables, setting switches, or using paper tape or punched cards. But the instruction set that we programmed in was effectively a mirror of the digital logic. We couldn't do anything beyond it. We couldn't synthesize larger things. In the 1950s and 60s, we introduced the intermediate layer of the microarchitecture to ease some of those big programming complications. So the microarchitecture provides a standardized mechanism for the instruction set to expose so that the programmer understands the order in which the instructions they provide will be fetched and executed, as well as the ability to provide some greater functions that may not be directly there in the digital logic. But realistically, the microarchitecture is working on a smaller instruction set than the instruction set architecture layer exposes to the programmer. In the 1960s, we start to see the emergence of operating systems. Now, before this, computers were operated by some kind of staff. If you wanted to run your program that you'd written and punched your cards as correctly as you could, you would have to sign up for a time slot where your cards could be executed. You'd show up, hand the cards to the operator. The operator would load them into the machine. Then the machine would start executing your code. Inevitably, your code would not perform correctly, probably with some kind of crashing bug. And the operator then would be responsible for getting up, going to the machine, making a dump from the machine, which effectively means getting another set of cards punched that represent the internal state of the system wherever you were in your program. And then they remove the two sets of cards, your original cards and the dump cards, bind bundle them together, hand them back to you. You investigate those cards, figure out what went wrong with your program, and then you try again. So that's what we had before operating systems. And the earliest operating systems that really helped us improve the overall throughput of our machines were really simple batch systems. And this was effectively a mechanism by which you would still bring your cards to the operator. The operator, instead of waiting for everything on the system to already be done, having done a dump for the previous user and pulled those cards off, the operator could load your stack of cards into something like a conveyor belt, a hopper of additional sets of cards, so that when the currently running program stopped, it could be automatically dumped if there was some issue, and those cards could be removed automatically into an output hopper, and your cards could be loaded up mechanically and then executed. So this improves the throughput of these systems greatly, which also improves the return on the investment of the cost of such a computer. Beyond this, we started to develop time-sharing systems, and the first of these, I believe, was developed at MIT. What a time-sharing system did was it allowed a central computer to be connected to a number of individual terminals. Different users could be at each of the individual terminals, accessing that central computer at seemingly the same time. But the reality is they would be hitting keys as very slow human beings, and those input stimulus would happen at unique moments. And the computer would, the central computer, the mainframe computer, would deal with each of those stimulus individually. So everybody would get a little time on a computer that was constantly looking for new inputs. And then when you finally got your information typed, your data in or your code in, and you tried to execute it, if it wasn't trying to look for user input, it would give each of those individual terminal users a little bit of time on the CPU for execution, which is very convenient. Now in the 1970s, we needed more powerful systems, and we wanted to write more powerful programs, but it was very difficult to manufacture these systems. There was a lot of human labor still involved, or the great majority of the labor was human labor. It wasn't mechanized. And so we became very clever, and we decided, okay, well, we can make that microarchitecture layer something that we can also write software for. And by doing this, we effectively increase what is exposed by the instruction set layer. So the instruction set layer is now no longer a reflection directly of the digital logic layer, but it's extended to include additional things that make programming simpler. So as an example, if the original instruction set of a machine would have included an instruction that could add two register operands together, we would find that in an awful lot of programs, particularly whenever we do basic counted looping, the kind of thing where you might have a for loop where I starts at 0 and then goes until as long as I is less than something. Such a loop typically involves an incrementing of I or a decrement of I. And with a microprogram, we could introduce a virtual instruction. We could say in the instruction set architecture layer that there exists an increment instruction, and it only has one operand instead of the addition instruction, which has two. But behind the scenes, the microprogram will implement or manifest the request to do an increment by using the low-level digital logic instruction that's exposed for addition. It'll just guarantee that one of the two operands is set to 1. Now, we also see the introduction of floating point number support introduced at this level. So it's not in hardware, it's being introduced in software. We even, in extreme examples, see instances of a microprogram that provides audio and image instructions. And this begins to push the borders of what we might even consider to be an operating system. Now in the 1980s, microprogramming loses its dominance, right? And the speed of machines increases tremendously as hardware takes control of the data path. One unique thing that happens by the 1980s is we change our ability to manufacture the components of our computer systems. In the 70s and earlier, human beings are putting the wires together. They're threading magnetic core memory, right? But by the 1980s, the manufacturing processes for the components of the computers, which we'll talk about in a separate video, that process is improved so that we can more efficiently create smaller, faster components to the computer. So now when we want more interesting capabilities in a machine, we don't have to worry about the human cost of manufacturing that machine. Instead, and then writing the microprogram to control that thing to make it seem like it's a more advanced machine. Instead, we can just design the more advanced machine and then mechanically produce it. That's why the microprogramming starts to go away, and instead hardware controls the data path. So history repeats itself. We start out in everything works just in the raw hardware. And then we get wise and we add some software control to the hardware below the actual software we are writing. But then we go back to a all hardware model, and we're seeing that kind of thing fluctuate throughout time still. Now, I'll remind you, this is like all kinds of things in computing history. So an example that I have here is machine code versus bytecode. So in the beginning, of course, our programs were all just machine code, and they ran right on the hardware. Over time, however, we introduced something called bytecode. So a long time ago, with a language called Pascal, the concept of P codes, or portable Pascal codes, were introduced. So you would write your high-level software, and instead of translating it down to the machine language, we instead translated it to portable P codes, bytecodes that could then be run on multiple architectures inside of a Pascal P code interpreter. This is very much the same model that we see today with languages like Java, but it fell out of favor and then came back. Think about time-sharing systems that we just talked about, these operating systems where there was a central computer and we had lots of little terminals where different users could connect to it directly. The terminals themselves didn't really do that much. You know, they made sure your letters stayed on the screen the same, right? They kept control of the monitors and so on. But really the computation was happening off on that central machine. How is that different from modern network services or web-based applications that we use so often, where we're really accessing stuff in some remote location? And our very expensive computers, of course, are basically doing a whole lot of making sure the pixels on the screen stay the same. Right? Checking your email is all really doing stuff from some remote location, using Google Docs, things like this. Right? So time sharing is a lot like modern network services, and a lot like modern cloud computing. Now, we have plenty more analogs to this history repeating itself concept. So I want to give one last metaphor, which I think is relatively interesting and has an analog in computing. And that's something from your great-grandparents' past. In olden times, families could own a personal motor. Now, it wasn't called a personal motor. I'm just using that term because it clearly connects it to personal computers. But families could purchase a motor, and it was a big deal. It was an expensive piece of equipment. And you would hook a bunch of peripheral devices up to this thing, like a pulley with a belt, or a washing machine, or something else. And then you could do greater things with this motor. Right? The motor's value stood alone, but through peripheral devices, it increased its grand capability for your family. This is interesting because, of course, then the personal motor goes away and everything starts to have its own motor because the manufacturing process for the motors brings down the cost of the motors and makes more of them available at large. Right? The same thing has happened in the world of computing, of course. We had big, very expensive computers and no one had access. And then when they became affordable, say in the 1980s, we see the introduction of the personal computer. And with the personal computer came a lot of power. But you could extend it by hooking up all these different things, you know, a camera or a printer or a scanner or whatever it may be, different joysticks, things like that. And in those early days, those peripheral devices were controlled effectively by the computer, for the most part. But just like the personal motor in today's world, while we still have all those peripheral devices, those devices themselves are now full-blown computers. In fact, in many situations, we don't physically connect them to the computer at all anymore. Of course, we've come to expect that via, say, Bluetooth or Wi-Fi or some other technology, that these devices can communicate, but we still think of them as being connected to the computer. Now, in the 1990s, we see the adoption of things like personal digital assistants. So we go beyond the personal computer that just sits on the desktop to a world where people start to carry with them computers that they actually use for computing, not just computers that are, say, a cheap quartz watch. So this is led primarily by two companies, Nokia and Palm. And the Palm Pilot was extremely popular until it disappeared with the introduction of really nice smartphones. But we also begin to see during the 1990s mobile phones become practically affordable. We don't really have massive adoption like we have today, where it seems everyone has a phone and everyone's children have a phone. But we really do see affordable mobile phones. And more interestingly, we start to see some convergence between the concepts of the PDA and the phone. So while the mobile phone, of course, has a computer behind the scenes, and a personal digital assistant, of course, had a computer behind the scenes, what's really interesting is we start to see some PDAs, and Palm provided one of these, that converged the technologies so that you could do double duty with the internal computer. You could do some software type stuff that were personal information management tools of the PDA. And you could also use the same device to make phone calls and do other basic telephony services. And this really gets us to the point where we start to see the precursor to the smartphone. And the first of these really is the IBM Simon. And you can see it here, where it's not just that the device is converged, but it's a device that really does some advanced things, both with the telephony and with the personal digital assistant tools. Now, in the 2000s and forwards, we are seeing, of course, massive penetration of smartphones. We all see smartphones in everyone's hands today. Mobile computers are everywhere. In fact, mobile computers are starting to replace desktop computers for many individuals and many families, in the same way that smartphones are replacing landlines for many individuals and many families. We've got a cultural expectation that we have access to high-speed networks, both wired and wireless, although now very few individuals look for the wired access because we really have come to expect some form of wireless connectivity. There's a big move towards web applications, and we see the growth of cloud storage and services. And possibly the most interesting thing to me is that we start to see the introduction of computers into almost everything that we interact with. We can't even have, I mean, we can still buy books, right? You can still buy a plain old book, but even books have become, e-books. And it's not just that you can download a book, but we have e-readers, devices specifically designed as computers to let you read books, even though you have other computers upon which you could read books that were in an electronic form. Right? The birthday cards I've mentioned before have things. Your anti-lock brake systems, your refrigerators, your toasters. The toaster is a switch that engages some heating elements, and after a small amount of time, ejects the toast, but we have computers in them. Right? The mere creation or the coining of this term, the Internet of Things, really demonstrates how this appears to be one clear vision of where we are going in the immediate future. And the Internet of Things doesn't just provide us great new capabilities that are all positive, just like a previous lecture where we talked about some of the downsides of software as an intangible thing. The Internet of Things opens up all kinds of new problems related to security, and so we must also keep a watchful eye on that. Now, I hope you've enjoyed this review of the major architectural changes, the organizational changes of machines over the years. In a future video, we're going to review the same kind of thing, but from a slightly different perspective. We'll look at technological generations of computers.